Let's kick things off. First of all, hello, and welcome to our latest webinar, Modern Industrial Modeling Made Easy. I'm JuliaSim, the head of marketing for JuliaHub. Before we get started, I want to mention that we are actually having a very special event tomorrow, April 6th. We're thrilled to be sponsoring a conversation with Bob Metcalf, who is the 2023 Turing Award winner. And he's also the inventor of Ethernet, the founder of 3Com, a research affiliate in computational engineering at MIT's Computer Science and Artificial Intelligence Laboratory, and he's working with the MIT Julia Lab. He'll be speaking with our co-founder and MIT Department of Mathematics and CSAIL co-founder, Professor Alan Edelman, tomorrow online in a webinar. If you're interested in learning about hearing them discuss the possibilities for Julia, future of innovation, please visit juliahub.com/company/events. You'll see it, and we'd love to have you join us. We'll be taking questions from the audience and look forward to hearing what Bob has to say about his visions for how he plans to use Julia and the differences it will make. Now let's get into today's event, Modern Industrial Modeling Made Easy. We're joined today by our presenter, Jacob Ververka. He's part of JuliaHub's sales engineering team, who helps introduce customers to the latest SciML techniques and really just get people up to speed on the products. Before joining JuliaHub, Jacob spent 6 years building applications and services for simulation and modeling workflows. So he's an experienced guy. I'll turn things over to him to kick off the webinar. Jacob.
Thank you, Misha. And while I'm kind of introducing the topic for today, Misha's going to paste a link in the chat. This is to a public repository where you can see some of the code I'm going to run, and then as well as some static markdown files should make it easy to read on GitHub. So if you want to follow along there, that's great. If you want to review that material later, that'll be there for you. So as Misha said, I've worked a lot around HPC, a lot around modeling simulation. What I'm going to go over today is really a entry point. So I'm going to introduce JuliaHub, JuliaSim, what they are. I'm not going to go in depth on any one feature, but instead kind of talk about the broad workflow enabled by these products and talk about each different area of simulation modeling, because this is meant to be a one-stop shop, a fully featured modeling simulation platform. So I want to show how how engineers can benefit from this workflow, and also how we can leverage some of the different platform tools to make maybe your job easier in some ways that you're not currently able to leverage. So with that, I'm going to be running this from within a JuliaSim IDE. So if you're looking at JuliaHub, this is an application right here. We can launch this, and then we're going to be greeted with VS Code in the browser. And with that, I'll get started. So a very quick, what is JuliaSim? I think that we can kind of start there and then. So JuliaSim is a next generation cloud-based simulation platform. What does that mean? I'm going to break that down into 4 kind of broad steps. We're going to look at how do you build models that you can run in JuliaSim. How do you optimize those models? And then as well as how do you create surrogates from those models? And a surrogate is a fast approximate model. So we're going to actually use machine learning to train a new model over many different trajectories of your original model. And we're going to take that training data and we're going to create a new model, which is reduced order. So it's going to run quicker. It's going to be close enough to our original answers that we can use it for inference later on. And I'm going to walk through these steps. As I said, each of these is kind of the jumping point. So this is perfect if you've not really dove into Modeling Toolkit and Julia at large, and you're kind of interested at what JuliaSim has to offer and what it looks like working with it on the platform. And so we're going to start here. And what we're going to do is we're going to build an RC circuit model. And you can see the diagram down here. That's what we're going to build. We're going to build this using the Modeling Toolkit standard library components. So again, good way to kind of get started is we're going to enable the environment. We're going to load these packages. I'm going to set some starting values for the resistor capacitance and voltage. And then I'm going to declare my independent variable here is going to be time. Now I'm going to create each of these components. So we can see from the diagram, we have a capacitor, we have a resistor. We know that we are going to have a source, voltage source, and ground. And these are all the things that I need to create this diagram. Now, these components are coming directly from this modeling toolkit standard library electrical component. And if I want to, I can get some help by in the REPL. Looking at, for instance, tell me more about the resistor. So in here, I can see what its states are, what its connectors are, what its parameters are, short description of the component. And this is going to help as I'm going through getting comfortable with modeling toolkit and the standard library, what's available here and what do I have access to? So what are its internal states? What are its parameters? I just access the help here in the REPL, but you can also do so. There is a Visual Studio command to show the documentation. So yeah, if you show documentation, you'll get the same thing and pop up here in the window. And this is, like I said, really handy as you're getting acquainted with the standard library and trying to figure out how these components work and how to kind of string them together. But let's move on. Let's continue to build out these components. So the next step is to connect them up. So I have a resistor, I have a capacitor, but then how, so far we have not described anything as to how this electrical current is going to flow through the system. And so we do this with these connect statements. This is coming from Modeling Toolkit, and it allows us to connect one state to another. So here I can see that I'm connecting my constant output. So this is the voltage. This is the voltage for the source. And I'm connecting the positive pin of the voltage of the source to the positive pin of the resistor, the negative pin of the resistor to the positive of the capacitor, and so on until I get to the ground. So this is going to create all my connections that I need. Now, in order to fully describe the model, I'm gonna do so here. So I'm going to create an ODE system, and that ODE system is going to be comprised of the connections that I just defined above, my independent variable, and also each of the systems that I have created above, because each one of those has internal states and parameters, right? So we need to know, our system needs to know about all of them, not just how they connect together, but what's happening in each of those systems. And so this is how I'm going to create this new model. This new model has this name, RC_model. So this is the output. Why don't I just clear the screen so we can kind of get a good look at what's going on here. So I can see that I have some equations, I have some states, some parameters. I can even take a look at just the equations that were produced running this line, so I can expand the connections and get the equations out. And that's going to tell me everything that I've described above. But this looks fairly complicated for an RC circuit. So what I want to do next is run the structural simplify command. And what this is going to do is algebraically simplify what I've passed in. So I have those 22 equations. I think it can be simpler, and I want it to be simpler. I want a performance system to run my simulations with. And when I run structural simplify, I can take a look at the equations of this new system, and I can see, in fact, it's reduced all of this down to a single equation. And this is that of an ideal capacitor. So this is a great way for me to work with these components in a way that's intuitive for me, right? I know I need a resistor, capacitor. I know how I want them to connect. I want to think about modeling my system in this way, not necessarily, mentally stripping away everything that I need and making sure that I do so in a way that when I'm performing my inference or my analysis, I have access to all those kind of intermediate things. I want to just describe the system as I know it. And then I want a tool, here it's Structural Simplify, that's going to give me the performant code out by default. And so that's what we've done here. And we've taken something, the original model, 22 equations down to 1. And this looks like it should work for us. So all that's really left to do is we have our system. We're going to define a new problem with the system, and then we're going to solve that problem. So here I define the problem, pass in my system. This is the time span that I want it to run over. And then I create the solution object. Looks good. So now I can plot the results. And something interesting to note is, if I go back down, is how I'm accessing these variables. So I can see here that I passed as an argument to index these. I want the voltage of the capacitor and the current of the resistor. And indeed, that's what I end up getting out of my result, right? So this is a great way to, like I said, get that performant code, but build up your model logically, intuitively in a way that we think about these things, not just in the way that we want the final computation to run on a supercomputer. So that's our kind of first example. And we've done this purely with built-in components from the standard library. So everything that we used here, it came from the Modeling Toolkit standard library electrical component. And then we also use this constant that comes from blocks. So we've got a few different components. There's thermal, electrical, kind of the basic building blocks module. And we can get pretty far with just those standard library components. But next I want to take a look at what happens when we need to expand on what's in the standard library, because this is very common. So a lot of our customers find themselves in the situation, right? They model and perform simulations in a particular domain, and they have strong opinions on how those should be executed. So they want really fine-tuned control over what that model's doing and how it's built. So this example is building a Chua circuit, and we find ourselves in the place where we have almost everything that we need from the standard library, but we need to build one more component. So if I just clear this out, make some room, and let's make sure we have all of our libraries loaded. So I know I'm going to use the electrical components. I'm going to use inductors, resistors, capacitors once again. But I want to build a nonlinear resistor. And I've included an image in the repository, which shows what exactly that's going to look like. In fact, I can just pull that up really quickly right here. So this is describing the relationship that we want our nonlinear resistor to, the behavior we want it to exhibit, right? Where GB and GA are the conductance ranges, and VE is our voltage limit. So I'm going to build our nonlinear resistor that we're going to end up using to fill out this Chua circuit. And after I'm done with this, I'm going to create a new object of it and connect all those together in the way that makes sense for our circuit. But to do so, let's take a look at how do we build this thing out. And I'm going to actually build upon something that's available from the electrical component library of the standard library. And so this is a component with 2 electrical pins, positive, negative, and current I flows from P to N. And we have 2 states, voltage and current. And so I can use this as how I describe that diagram that I showed of the behavior I want this nonlinear resistor to have. So I create this 1-port component. I'm going to unpack its states. So here I grab V and I, and now I can just work with these directly in my equation. Here I'm going to take, I can alter these when I'm creating the resistor if I like. So I'm gonna fill in my conductance and my voltage here, and I'm gonna make these parameters as well. And now that I have everything, I have all the parameters and all the variables that I need, I can just write my equations, similar to how I would on pen and paper. And this is a little bit different because we are going to use if-else statements because we kind of have 3 branches, right? So basically what this is saying is if my voltage is below that voltage limit, then I want this to be the behavior. Otherwise, if my voltage is above that upper limit, then I want this to be the behavior. And if neither of these 2 conditions are true, if I'm within the limits, then I want this to be the behavior. So I can take this, it's a single equation technically, but this kind of complex behavior, I can create my new ODE system, and this is going to give me that component that I need to use to build out the Chua circuit model. And we can see that down below. So let's execute this. Down below, I'm going to now create all my other components. So my inductor, resistor, 2 capacitors. I'm going to create my nonlinear resistor and my ground. Now I connect all these up. Very similar to how I was doing before. We're not going to walk through that. And now again, it's time to create my system. Now, remember last time we created the model as just an ODE system where we provided all the connections that we made, as well as all the systems that we're using to make those connections. Let's do that. And then it looks like we have 38 equations. And what happens when we structurally simplify this system? Now I have 3 equations here. So this matches what we know to be true of the system. This is really all that's needed to solve this. And again, this is that performant version of the code that we want to be running. But I didn't have to come to that conclusion from the start. I could describe each component in the way that I can actually end up testing this to make sure that it exhibits all the behavior that I want under different conditions. And I can build out an entire library of useful components for my own domain, and then reason about my models logically to come up with these larger, more complex models. And once I do so, I just, I have a system that I can formulate an ODE problem and solve it and analyze. So this is the general workflows, how you're going to build out models. And this is how you're going to extend upon what is in the standard library to fit your use case. And so now I've kind of walked through how do you build these models. A next logical step is when you find yourself in the optimization part of the workflow. And we have JuliaSim Model Optimizer here. So we're going to scratch the surface of what we're going to, of one use case with Model Optimizer. But in general, this is something that allows you to perform calibration, parameter estimation, create virtual populations of large data sets and large models without necessarily advanced programming. So this is a package which allows you to scale these workflows to larger and larger models and data sets, and still get certainty of the answer. So here I'm going to load the package. I've got a few others to load. Let's make sure they're all available. This is the exact same example that I just walked through. So we don't have to re-execute this because this is the Chua example that we just stepped through. And really, we left off at this point. Excuse me. So I've created my problem. I've got a solution. And now we're going to start speaking in terms of JuliaSim Model Optimizer. And the big term here is the inverse problem. So we are not in the situation where we want to know the solution given some input. We actually have we have real world data and we have our model, and we want to find all of the different combinations of parameters where we can fit our data, our model to our data, and do so in a robust way and leverage distributed compute for larger models. And so just to grab some data, I'm going to take that solution object and I'm going to create a data frame out of it. So not too much is going on here, but you can see what this looks like. It's got timestamps and it's got my state. So now I'm going to create what we're calling a trial here. And this is an experiment. So this is, one example of what this system looks like with the data that we want to fit to over the time span that's running. So I create that trial, and now to define that inverse problem, I'm going to specify all of the different real world, observable cases that I have. Here's a list of one, but I'm going to pass as well my system. And then I'm going to pass this last argument is pairs of parameters along with their upper and lower bounds for how I want to create this virtual population. So I basically want to say, fit this model to this data where these parameters are somewhere within these bounds, right? And already I know that it's going to be really hard or impossible to come up with just one answer for this. So what I want to do is create a virtual population. And really quickly, let's get right here. So this is what the result of that looks like. I can see that these answers are within the bounds that I defined, and I can see they're kind of converging on what I think might be a good answer. To represent these together, I'm just going to form 3 different plots and then plot all of those together as one. And what you're seeing here is the density of the virtual population that I created, the dashed line with what I know to be true, and we're seeing how that virtual population is capturing the actual value that we're after. And just I guess take note, this is a small example. Close this, where we're keeping our iteration number low and we're keeping our population size low. So this is really just to illustrate the type of workflow that this is going to help you perform, right? We have other examples out there of how to calibrate large building models, and there's a few others in the documentation as well. But this is where JuliaSim Model Optimizer is going to help you. You built your model. Now you want to actually take a look at, how do I calibrate this thing? And the next thing that we find many people need, many engineers need across industries, is they need a way to accelerate this model, because it just takes too long for the inference they want to perform. And that's where JuliaSim surrogates comes in. So again, what we're doing with surrogates is we're following a similar process where we can take actually multiple inputs. We can have just code, and like we do in this case. We can use functional mockup units, or FMUs, which are they're binaries of the model along with a model description in XML format. These are things that you can export from other modeling tools. And so whether you want to, on a greenfield project, start from scratch, write your model in Julia, build up your component library, and define your model, or if you want to take a model that exists in another tool, export that FMU, we can plug that into JuliaSim and attempt to create an accelerated model. And I want to highlight here the steps. They're the same whether we're working with code or an FMU, or just pure data. We're going to define our problem, and then we're going to perform the data generation step. And all this means is that we are going to gather many trajectories of that original model. So we're going to run it under all the different circumstances that we can kind of think of that describe the case where we want to run our accelerated model in production. we're going to take all that data that we generated, and it's going to be used as training data for our surrogate algorithm. So we generate a bunch of data and we train against it. And that training process is something that we're going to walk through here. So let's import JuliaSim surrogates, ordinary diffeq. And again, here we're going to work with code. So here I'm just going to create a simple function for the lockup Volterra model, and skipping over the actual, the dynamic system, I want to talk about how do we start to generate data. So here we use a terminology called sampling spaces. So all that means is, your model has some parameters. Over what range of values do you want those parameters to generate data for? In other words, what do you expect to encounter in the real world? What parameter values do you expect that model to need to handle? And so after I create my problem, I can start thinking about this sampling space. And in this case, I'm going to say that I want to generate 2,000 different samples for this parameter space. And I have 4 parameters: alpha, beta, delta, gamma. I want to define my lower and upper bound for each of those. So what makes sense? What breadth of values do I think that this model needs to cover? Set the upper and lower limits there. And I could do the same thing for an initial condition space as well as for a control space. But for right now, let's just work with one. And let's talk about how we're going to generate this data. Because it's not necessarily, it's not a trivial problem of, how do I run 2,000 of these, make sure that I am, keeping all the results organized, that I can aggregate over them later and use them as valid input for training. So the method that JuliaSim Surrogates offers for this is a simulator config. So this is a configuration for simulating every one of those trajectories that you're describing with your sampling spaces. So here, I first create a parameter space, and I do so just by passing in that lower bound, the upper bound, and the number of samples. And then I'm going to create my simulator configuration just with that one sampling space for now. And I also have a nice way to kind of review the summary descriptions of, what this space entails. And if I had defined my initial condition space, my control space, I'd see something similar, right? So this is a handy way to make sure, at a glance that I'm covering those scenarios I know that I need to cover. Now I have a simconfig variable here. I can call this on a given problem, and I can pass different solver keywords, which is going to solve this problem with those keywords, essentially across all of the different configurations of this simulator config. So in other words, this is where I'm actually generating that data. So let's run this. You can see it's going to take a little bit of time. It's 2,000 samples. It should go fairly quickly. And let's take a look at the compact version of the table, which is still a little too big because I'm zoomed in here. But we get a very similar table to what we saw when I displayed simulator config. Now I get some statistics on my experiment data. That's why we've named this ED. This is what we're calling experiment data. So this experiment data object is what we need in order to train a surrogate. The really interesting thing that we're going to see later is that this experiment data, again, can be generated through a very similar convention, whether it's from code, from an FMU, or from just pure data. But for now, let's move forward. We have one final step. We've generated our data. Now we want to create our surrogate. So to do so, I need to establish a reservoir size, and I need to decide which model I'm going to use to train the surrogate. So here, I'm going to use a CTESN with 100 size for the reservoir, and I'm going to now call surrogatize on my experiment data and my model. So all the data I generated, which surrogate algorithm I want to use, and I want to save the results in this surrogate variable. Okay, we're done pretty quickly. And now we can take a look at the surrogate object, very similar to the sim config, is now something I can call. It's very also similar to a solution object. Back when we were just creating the problem, solving problem, we have that sol object that we can call into at different times. And it'll give us an answer even if it didn't solve at that specific time step. This is going to do something very similar. So you can think of this as having that common solution of U and P and T. U being states, P being parameters, T being time. And so now I want to say, get the answer of the surrogate with these two initial conditions, these parameter values, which are within my upper and lower bound that I described above, and over this time span. And then we can see there that I get my results out. So this is the workflow that you're going to follow for creating surrogate models. And I have another example here where I do the same thing with an FMU. And I'm just going to point out the differences as we walk through this, because there really won't be that many. We're following a similar convention. So keeping in mind what we just did, let's set up a very similar environment here. Notice the difference is that I am going to be working with an FMU, so I need some ways to import that model to gain some descriptive information about that model. So I'm going to do that. So now I need an FMU, and in order to do, there's different ways. So you could take your FMU on your local machine and you could drag and drop it right here into the file browser of your JuliaSim IDE. That's perfectly fine. I am going to load a data set from JuliaHub, and I'm going to write that to my local, to my local path here. This is actually it because I've already run it, but we can do it again to no harm. And what this is really helping is to make sure that this is reproducible. I don't have to make sure that I have this in place before I run this. I don't have to make sure that I share this with a colleague if I want them to, take my work and tweak it or draw their own conclusions. As long as they're logged into my same JuliaHub instance, this will work for them. And now I just want to load that FMU. Great. And now I'm going to create my sampling spaces. It's a very similar process to what we did before. Tell it how many samples, give it an upper and lower bound, and then let's create a simulation configuration. And I get some statistics for what I am expecting to generate. And now when I generate my experiment data, it's a very similar process. I pass in the model. In this case, it's that FMU. And I just have some different labels here that I'm drawing from the model description of the FMU. That's still a little bit too big to render nicely in the screen. But here I am at the end where I have an experiment data object. I generated it from an FMU, but it's going to work the same way when I actually want to create the surrogate object. And so here again, I'm going to create the surrogate with a reservoir size of 100, a CTESN model. And once I've done so, I can call into the surrogate object to get, to get the results. And this is how I want to perform inference with this accelerated model, right? I'm skipping over a lot. There's a lot of questions around, how do I know that this is accurate enough? How do I, try to gain sufficient speed from surrogate model? And these are all great questions, but this gives you a good idea of what this workflow is like and what it's like to work with, after you have your model in place. How do I actually describe the scenarios I want to train over and then train that new surrogate model? And as you can see, it's a really not a lengthy process. A lot of the effort is going to be in, analyzing this and making sure that you get that speed and accuracy to the point where you want. But this last point I think is interesting because when we get there, what happens, right? I don't want to run the script every single time I want to perform some inference. I don't want to incur that training cost or the cost to generate the experiment data. I just want that surrogate object. And so I'm going to use two different mechanisms here. I'm going to use the serialization package, and I'm going to serialize that surrogate object. And then I'm also going to use the JuliaHub client package to upload a new data set. And so I've already done this, and we can kind of see the proof there. Excuse me if yeah. So if you see here, oh, I don't want to save. If you see here, you can see the surrogate object, or the surrogate data set, excuse me. And I have two little buttons here. I can either use this data set, in which case it's going to give me a pop-up window in the bottom right to copy a data set command. So I can copy that command. And I think might have to, yep, okay. Well, it says it's not found. Well, it should be found. But anyway, I can see here in the JuliaSim IDE, as well as in JuliaHub, I'll show you later, where now I have this new surrogate object. I can click this download dataset button, and it will download it to my working directory. And just to make sure that this doesn't overwrite something, so you kind of see, yep, so there it is. This is something that I can load in, because it's a serialized object, right? So now when I'm working with this in the future, I can just deserialize that object and then call it like I did before. And I can skip all the training, all the data generation. And the beauty of this is that the JuliaHub client also provides there we go. So I can upload new dataset versions. I can upload new datasets. I can alter the metadata of an existing dataset, as well as download like we saw before. So as I'm working with this, I can iteratively tweak my parameter space or any of my sampling spaces. I can generate more samples. When I feel like I have a new surrogate that is potentially a better fit for my production use case, I can upload a new version of that data set. And now that's available for me or anyone else on the platform that I give access to that data set to perform inference. And this is where I want to take a step back, because I've shown you now a lot of the high-level JuliaSim features. So we've walked through, how do you build a model? How do you perform some optimization workflows on a model that you built? And then how do you accelerate different types of models, ones that you've written the code, and ones where you're importing from an existing tool? And we see here that we can leverage the platform to save a little bit of work. So I don't have to undergo this training every time. I can save this out. I can save it as a data set and allow other people to just load this and run it, and they may never have to incur the training cost. And I'm going to walk through just a couple platform features that I feel do really make this a nice modeling and simulation platform, because you're never just going to run one model, right? You're going to be working on this model iteratively. It's going to be a process, and you need a good way to make sure that you're keeping track of your work. You have a good way to share this with your teammates, and that you also have reproducibility at every step, right? Because it's something built into Julia. Reproducibility is important. It's something that JuliaHub as a platform really makes sure that that we help engineers along their paths throughout the modeling journey. So if I just open up this, for instance, I'll just close some of these. I want to just really quickly walk through what this code's doing. Let's actually look at. There we go. So here's a very similar situation where I'm going to build my model. And I can use the Julia logging macros to, give me some information what's going on. Maybe this is a really long running job, and I want to see what's happening under the hood, because what you've seen me do is work interactively. But actually here in the JuliaHub extension, you also have the ability to leverage distributed compute. So
Jacob, I think you need to zoom out a little bit to show a little bit more of that.
Sure thing. And let me just close this. How does that look?
If you're trying to show the left-hand column, it's a little cut off.
Okay. I need to zoom out.
Yeah, zoom out one more time. I think that's a little better. Can everybody see that? Okay.
Thank you. So here we can just see that this gives me a way to take this script. I'm going to tell it to use the current script that I'm on. And there we go. We can see it updated. The bundle directory is the directory where it lives, just in case I have any other scripts or code or data that I want to submit with this job. But this is the extension that I'm going to use to execute batch jobs. So I can right here very easily say that I want to run a distributed job on CPUs or GPUs. I can configure the types of machines that I want to use. So here I can say that I want I want machines with 8 virtual CPUs and 4 gigs of RAM per vCPU. And then I want to run one Julia process per each node or per each vCPU. And if you look down here, so right now it's selected on node. This sentence down here is helping me kind of keep track of how these selections end up affecting the number of workers that I have to compute this problem. So if I change this to vCPU, now I have 39 workers, and that's because I have 5 nodes here selected. So if I just drop that down to 2, so I have 16 virtual CPUs. I have 2 nodes, each with 8 virtual CPUs, but one of them is a coordinating node, and then I have 15 worker nodes. So again, this gives me a really nice way to take these scripts, run them in batch. I can set cost or time limits on them. I want to run JuliaSim images here because, well, actually not in this case. We technically could run with Julia, but anytime you're going to say using JuliaSim Model Optimizer or using JuliaSim surrogates, you want to make sure that you're running with the JuliaSim image. And then I can, give it my name. Whoops. And then I can also provide inputs. So here I can provide key value pairs. And if we just look at this portion of the code here, so I can provide a key value pair where this is my key. And then I provide some value. And let's say that this time I don't want to run it for 3,600 seconds. I want to run it for 72. I can do this for what I'm calling variables input X, Y, and Z. And then when I run my job, it's going to take those variables. If I don't provide them, it's going to use the defaults that I provide here. And if I just show you what this looks like on the platform, I actually ran a few earlier with that same RC circuit that I was using in the first examples. So if I hit this drop down, I can see my key value pairs for those inputs that I provided. And I even changed the name to make sure I could kind of keep track of what I was changing. So right here, it provides me an easy way to go back, look at all my runs, my job runs that I've performed. So I could submit many batch jobs at once, come back, view the results, and I can also make it easy for myself to pull these together. So if I click details, and so here's my Inputs, okay, I don't have any outputs for this job. I need to select another job. But I can monitor my resources. Here, I just ran it on a single machine, so you only see one set of resources. But if I go back really quick, and let's just walk back a couple days. Yeah, this should have what I need. There we go. So you can also see that I saved a solution. I saved an image of my plot. So I can download that right here directly. I also defined outputs. So again, kind of at a glance, I can come here and I can look and I can see what are the outputs from this run. And those outputs are defined very easily here. So I'm just going to create a Julia dictionary with some symbol keys, some values. So here I'm saying, what was the return code of my solution? What was my final value for X? What was my final value for Y? And then by saving this JSON dictionary as the results environment variable, I'm automatically going to have this information when I look back on this job. And in a similar fashion, I have a results file environment variable. And this allows me to save either a single file. In this case, I'm just saving my plot. But if I make this path a directory, it's going to zip up that directory and save everything that I had. So I can save those results, or I could also use that same mechanism I showed before and actually upload a new data set. So how you want to work is really up to you, whether these are long-lasting results that you feel you're gonna leverage in the future. But JuliaHub as a platform does provide you with these different ways to work interactively, kind of work out the model, figure out what all the dynamics are you're trying to describe. Then when you're ready to scale and you want to start running this on on a larger cluster, or when you want to just start shotgunning some different parameter values, or even perform some of these different optimization or surrogатization workflows, you can do that in batch, save all your results as data sets, and then in the job, you're going to maintain the script that you submitted to generate that. So this is the script that we selected here. And then everything in this bundle directory gets zipped up in the star file. So you're always going to be able to reproduce this. And here's the project and manifest files as well to make sure that you know exactly which packages you were depending on and which versions you were working with. So really every step along the way, you can save your results and have confidence that you can go back and reproduce those results. And then, your colleagues as well can just be working with your most recent version of your model, for instance. If you're going to update new versions of data sets and point them to working with a data set. So just again, showing you what that looks like from JuliaHub. Here is that data set that I created in that last script. So this is that serialized object. Right now, I believe, where is it? Yeah, right now this is private. I can make this public, and then anyone working who has credentials to mycompany.juliahub.com, I can make it so that they have access to this and they can start performing inference with this model. And then as soon as I send a new version, they can start working with that new version as well. And let me just also point out, kind of walking back. So we talked about how do you build models and the fact that it's likely that you're going to want to build your own components. So what you're seeing here is kind of the interface. This is what it looks like to search packages on JuliaHub. It's got a great package search, and you can find symbols and keywords and whatnot. And then if you click this read on JuliaHub link, you'll find that JuliaHub is also able to build and serve your documentation. So I don't know if you can see the URL, but it's at docs.juliahub.com/modeling toolkit standard library. So again, if this is your company JuliaHub instance, this is something that you can create your component library, create all the documentation. You can host this private registry on JuliaHub, and then the folks who have access on your team, they can look at the components that you're building. They can look at the data sets that you're building. They can read the documentation, and all of this is going to live on your company instance. And something we didn't get into as well, but you can share your ideas through notebooks as well. Again, making them public or private. And that, I think, kind of rounds out the story of JuliaHub and JuliaSim. JuliaSim is a way for you to get these really advanced modeling simulation features, and they're meant to scale. So as your model, as the complexity of the system that you're building increases, all of these offerings are going to scale, and they're going to work on distributed compute without writing a completely different version of the code that works distributed. And then JuliaHub is really always there as the foundation to make sure that with that advanced modeling work that you're doing, you have all the capabilities you need to track the results that track the progress and the results that you're creating, and also share that across your organization. So I think that is everything I wanted to get through today. Again, it's scratching the surface of what JuliaSim has to offer, but hopefully it gives you an idea of what it's like to work on JuliaHub and some of the things that you can do with JuliaSim.
Thank you, Jacob.